Hi there, welcome back to this channel. And in this video, I'm going to take you through chain rule. So under this chain rule, you handle one type of cases. Okay, so this is case one. If this is the first time you've been on this channel, kindly subscribe and please watch this video to the end. So it says compute the z on the t, right, for each of the following functions. But before that, let me give you the whole overview of this chain rule. So this is a multivariable function, yes. But for the case one, it's very similar to what we did in calculus, that is handling only one variable. So let's see, if you have any function which is a function of xy, right? Then this function itself is taking inputs x and y. X is equal to another function g of t. So meaning the function is taking an input which is also a function, right? Then y is equal to, let's say, h of t. So meaning that this function here is a function of functions, right? So for us to effectively differentiate this function, we need to apply what we call the chain rule. So this is termed as a composite function. Composite function. So whenever you are having a complicated system of a function, you can break the function down into different parts, and after you apply the chain rule to solve the function. Okay, so now let's see, I have this function here which is taking inputs x and y, and each x and y are also function in their self, right? So if you want to find the f over the t, you want to find a change in f with respect to t, right? How do you get change in f with respect to t? To get change in f with respect to t, you can either get that through x or through y. Is that not it? Because x is also a function of t, y is a function of t, right? So to get change in f with respect to the t, meaning we have to enter our function, or we have to differentiate our general function here, right? So this will be equal to simply the f. Now, as I said, we can differentiate it with respect to t through two ways, either through x or through what, y. Is that not it? So we will first differentiate our function with respect to what, x. So this gives us access to what, x. Is that not it? So multiply by, now we go to the x itself, right? So it looks like you have to differentiate this bigger function to open the door to the internal what, functions. Do you get it? So you can only access the internal function with before by entering the bigger function, right? And how do you enter the bigger function? Is by differentiating that bigger function with respect to the variable you want to enter. Okay, so now I want to get to x. Is that not it? To get to x, I'll first open this door before I come to x differentiate with respect to t. Is that not it? So in the process of opening this door is the same as you differentiating this with respect to x. Okay, so now I've been able to differentiate this with respect to s. Then you simply differentiate your x with respect to what, t. So the x over the t, and obviously this looks like what, the x will cancel this and you are getting the f from the t, but x is only one part of this function, right? So you add this plus, now you can also get the f on the t through what, y, because y is a function of what, t. So what do? We need to access y through what, our function f here. So we can only do that by differentiating the function over the y, and this opens the door to the room of the y, or sorry, to the room of the function y. Then you multiply this by what? You differentiate this with respect to what? T. The y over the t. So this is how the chain rule is. This is how the chain rule is. So no matter the number of variables which are functions they give you, you just have to take it systematically. Ask yourself, how do I get my final derivative here? Maybe through x, through y, through z, depending on the variables of the bigger function. Once you get your variables down, the next thing to do is you are going to enter this bigger variable with respect to each of them one by one. then you multiply them by their respective derivative with respect to their what also independent variables, right? Yeah, so one way that it can help you is you know that you want to find the f over what the t, right? So first of all, to start, you just have to write the f here, right? The f here, and you know that you have x and you have y, so you simply write the x here. Then you bring this the x up, okay? You just carry this the x up so that it will become the x. Then obviously you know that if you want the f on the t and you've written the f on the x, you just bring the t, right? Plus the f again, then you bring your dy times your dy over the t. So you just apply the door opening principle. That's going to guide you, right? So maybe I want to go to x, or I'm finding the f on the t. The t is the independent variable of the x. So meaning I have to enter this gate to get to x. Then I will differentiate it actually. Entering this gate through x is the f on the x, and also differentiating this is the x on the t, right? So with this knowledge, let's quickly solve the problems we have here. So the first problem is compute compute the z on the t for each of the following. Compute the z of the or on the t for each of the following. So the first one is z is equal to x to the power e to the power xy. So a z equals x e xy, where x is what t squared, y is what t to the power -1. So this is the problem you have here. I've been asked to find the z on the t. So what is the z on the t? Now, where can we find t? Where can we find z? We can find z from here, right? From this equation, you can find z. Then you can find t as the independent variable of our what? X and our y. So meaning that I can only access t by opening the door of what? The major variable, sorry, the major function. Then once I open the door of x through here, then I'll come and differentiate the x itself. So you just simply say that the z on the t itself can be found on both x and y, meaning that we have two ways. Is that not it? For one for x and one for what? Y. So you just simply write the z on the x. So now we are opening the door of the x from the main function, okay? So the z on the x times the x on the t plus, now we are going to enter the main door through the y, okay? So we simply have the z on the y times the y on the t. So once you're able to write the chain rule, then you are good to go. We can easily solve for the rest because it's just normal differentiation. So what is the z on the x? So the z on the t is equal to minus z on the x. I'm differentiating this function with respect to x. This has a linear part and it has an exponential part, right? So for the linear part and exponential part, you're going to apply what we call the product rule. So meaning that I'll differentiate x maintaining this, and I'll maintain this differentiating x, sorry, and I'll maintain x and differentiating this. So differentiating x, I'll get 1, right? Then maintaining e to the power xy plus I will maintain x and differentiate e to the power xy. Differentiating e to the power xy. Now I'm differentiating with respect to x, so y is a constant, okay? So I simply have y e to the power xy, okay? Because when I differentiate x, it will be 1, and I'll just carry the coefficient of x down here. So this is only for the z on the x, okay? This is only for the z on the x, right? So we are getting this, the z on the x. Then now what is the x on the t? The x on the t is equal to, I'm differentiating this with respect to t. That will give me what? 2t. Is that not it? 2t. And this is all for the x part. Then you just add it to what? Your dz on the y. I just have to differentiate my major function here with respect to what? Y, right? So to do that, I simply have to analyze the function and know the approach I will use. So this here, you have the y as the exponent. So meaning this is just an exponential function for us to differentiate. X will be a constant. This x will also be a constant. For that reason, you just straight away apply the exponential principles for differentiation. We will differentiate the power, then you multiply the resulting by the entire function. So differentiating the power, we get what? X, is that not it? If you differentiate this with respect to y, you get x. So I'm simply going to have x multiplying x e to the power xy, then times our dy on the t. This is dy on the t. To differentiate dy on the t, you simply multiply it by what? Negative t to the power negative 2. Then we are good to go. So this is for the y side. Then at this point, my dz on the t is equal to, this is e to the power xy plus xy e to the power xy, all multiplied by what? 2t plus x squared e to the power xy times e times negative t to the power negative 2, right? So at this point, you realize that the function said we should differentiate with respect to t, not x and y. So meaning that at the end of this, we need to make sure that the only variable we are going to see is t. Okay, the only variable we are going to see is t. So wherever you see x, you put the x function there. Wherever you see y, you put the y function there. So our dz over dt is simply equal to e to the power. So the x is what? T squared, right? So t squared, and the y is t to the power negative 1 plus t squared t to the power negative 1 e to the power t squared t to the power negative 1, all multiplied by what? 2t. Is that not it? 2t plus x squared. X itself is t squared, so t squared to the power squared e to the power t squared multiplying t to the power negative 1 times negative t to the power negative 2. So this is another phase of simplification. Okay, so with this phase of simplification, you just have to open your eyes. So I'm going to get e to the power, I have 2 minus 1, so e to the power what? T. Then I'll have plus, this will as well give me what? T to the power 1, so t e to the power another t, all multiplied by what? 2t, right? Then plus, here I'll get t to the power 4, t to the power 4 e to the power t times negative t to the power negative 2, right? So my final becomes 2t multiplying e to the power t plus t e to the power t, then minus t to the power 2 e to the power t. And this gives me the derivative of this entire function z with respect to what? T. Now let's consider our second problem. So our second problem is what you have here, and I have, let me write it directly from my side. So I'll have b, z is equal to x squared y cubed plus y plus x, where x is equal to natural log of t squared, y is equal to sine of 4t. So this is it. He said find the z over dt. The function z is given as x squared y cubed plus y cos x. Our x is given as natural log of t squared, y is given as sine of 4t. So now you can, I always say that to start, ask yourself, where are my variables? Z is coming from the bigger function. T is coming from the smaller functions, right? So meaning that if you want to find a change in z with respect to the change in t, you first have to open this door of x, then we come to the x itself and differentiate t, right? So you differentiate your bigger function with respect to x. That will give you access to the t within the x. Then you differentiate the x with respect to t. Plus, you open the door here, okay, with respect to y, and that opens the door of what? Of y. Then we simply come to y and differentiate what with respect to t. As simple as that. So if you use such a scenario, it will help you all the time to simplify complicated ones than this, right? So to open the door of this with respect to x is the same as dz over dx. I want to get access to the t of the x, right? Then times, so once I find this, meaning I have access to what? X. So times the x on the t plus the same thing if I want to get access to what? Y dz over dy times what? Dy on the t. So right after here, you go by your differentiation. So if I want to differentiate this entire function with respect to x, right, any y becomes a constant. So with the first one, I'll have 2x y cubed plus y here is also a constant, so it should be, yes, plus negative sine x. So negative y sine x, let me do it well. So when you differentiate cos, it's negative, right? And this is a constant, so minus y sine naught x. And everything here is for the z on the x, right? So you multiply it by the x on the t. What is the x on the t? The x on the t here is a length function. So you differentiate what is in the argument. That will give us 2t over itself, t squared. That's all. All this is for what? The x side. We are now moving towards the z on the y. So for the z on the y, I'm going to differentiate this function with respect to y. Whatever I see as x is a constant, right? So when I come to the first part, x squared y cubed, when I differentiate with respect to y, I'm simply going to get 3x squared y squared plus, when I come to this side, cos x here, the whole cos x is a constant. When I differentiate y, I'll get 1. So I'm getting cos x. Okay. This is for what? The z on the y. Then we multiply this by the y on the t. The y on the t is a trig function, which is also a composite. So here, you differentiate what is inside, then you multiply it by what? The entire term. Whilst you are what? Differentiating the entire function as well. So when I differentiate 40, I'll get 4 out. Then you differentiate the entire function and you get what? Cos 4t. As simple as that. So from here, we are going to make our substitutions. Or you first break it down to the simplest form, then we apply your substitutions. Okay. So here you are going to have 2xy cubed minus y sine x multiplied by, if you have this t can go into here 1, so 2 over t plus 3x squared y squared cos x times 4 cos 4t. So with this, I simply make substitution directly, right? So I'll have the z over the t is giving us, wherever I see x, I'll put what? Natural log of what? T squared. Whenever I see y, I'll put sine of what? 4t, because we've been asked to find the z on the t. So I'll have 2 multiplying natural log of t squared y cubed, where my y is sine 4t cubed minus another sine 4t, right? Then I'll have times x here, times x. So that times x will give me natural log of t squared. Okay, yes. times 2 over t. This is substitution for only the x part. Then the y part comes as what? 3. Our s squared is now natural log of t squared all squared. Then the y is also sine 4t all squared. Okay. Then I continue from here plus this is what? Cos x, right? So cosine of natural log of what? T squared. Then everything here multiply by what? Everything within here multiply by 4 cos 4t. So in solutions like this, because the solution is very complicated, you wouldn't have to worry yourself simplifying it so much. Making this direct substitution should be enough so that you can get your score. Okay, so if you want to still go ahead and do some little substitution, you can multiply this. So this one, you are having 2 over t here, you're having 2, so you're going to get 4 over t, right? So okay, this, there is a subtraction here and minus sign here, so you don't want to just worry yourself. You can make some factorizations here. All right, so maybe you can get from here, you take 2, let's say natural log of t squared out, then you can take 1 of the sine 4t, and that will give us sine 4t all squared, right, minus 1 over t for the first factorization. Then here to cannot factorize, here the natural log is in the argument of the cosine, so I think we just have to maintain that. Okay, so with this side, 4 cos t is multiplying the entire thing, right? So within the entire thing, I have 4 cos 4t open brackets 3 natural log of t squared all squared multiplying sine 4t all squared plus cosine natural log of t squared, like that. And this becomes the solution for our partial derivatives, or sorry, the differential, but rather using chain rule method. As I said, this is case 1. So in our next video, we are going to do case 2. Then we'll do case 3 in the subsequent ones. Thank you for being with me in this video. Kindly subscribe to support and don't forget to like and share.